This is a bit of an intense lecture as we'll go through a lot of the math of equilibrium conditions and Legendre transforms, and hopefully get a little past that, dealing with the mathematical structure of thermodynamics. A lot of this is described in Callan chapters 5 and 6, but if you prefer, you can also read De Fontaine chapter 4. De Fontaine just always seems shorter about most of the things we will talk about. I often will give readings from both books. It's kind of up to you to decide which one you read. The thermodynamics is the same, you know, and this is not an undergraduate course, right, where I need you to do specific things in the readings. The readings are there just to look at the course material from another perspective. Sometimes they just give other commentary on it. So, but I will always fully cover things in lecture. So let me recap where we were. We defined equilibrium conditions, right, which started from the second law that the entropy had to increase at constant energy. We sort of proved the corollary to that the entropy, if you write the entropy as a function of the extensive variables, I'll just do a simple system here for the sake of argument, so we only have PV work, that's also minimized at constant S and V. And remember what I told you about what minimization means, right? When we say constant S and V, those are the boundary conditions. So what we minimize over is the internal degrees of freedom that are consistent with those total values of the extensive quantities. We then showed that the enthalpy, which is a function of entropy and pressure, so the entropy, which is defined as U plus PV in a simple system, is minimized at constant S and P. And if you remember what I told you, the reason you minimize now not the energy, but the energy plus PV is because if you work at constant pressure, you have an energy channel, a work channel through which you can have energy exchange with the environment, which is why you minimize not just the energy, you minimize this combination. And then we kept on going. We defined the Helmholtz free energy, which is a function of temperature and volume. So it's defined as U minus Ts. And again, that makes sense now. The volume channel is closed now because we're at constant volume, so there's no mechanical work. But since we're at constant temperature, we can have entropy exchange, and this is minimized at constant T and V. And then ultimately G at constant temperature as a function of temperature and pressure is defined with both energy exchange channels open, and so that's minimized at constant T and P. There's sometimes some confusion about the minimization of these potentials. So in equilibrium, they are actually all optimized, so minimal or maximal. It's just depending with respect to what variables you optimize them. So let me sort of state that slightly more concretely. Let's say you have a system under constant temperature and pressure, and you let it equilibrate, and so in equilibrium, it finds some state, I'll call that star. That's the equilibrium state under constant temperature and pressure. So you would do that, you would find like, you know, you would write down G, right? And you would find the state that minimizes G. So that state has some values of entropy and volume, which I'll call S star and V star. So if I now take a state, if I now take the system and I constrain it to S star, V star, so now I constrain the extensive variables rather than have applied intensive variables, this state, equilibrium state, is exactly the same, right? So this also goes to state star. By definition, right, because S star, V star belong to state star. So all I'm doing here is I'm writing the same equilibrium with different boundary conditions. Think about it this way, right? If I let the volume equilibrate in a constant pressure environment, and then I constrain that volume to the equilibrium volume, I'm not doing anything, right? I'm not really adding a constraint. I'm just, because I'm already in the equilibrium volume. So technically all these potentials are minimal in equilibrium. It just depends on how you write how you consider the boundary conditions on the equilibrium. Each function, I've written out what the variables are of each function. These are called the natural variables. And the way you find them is from the differential. So let me do that for enthalpy. So H is U plus PV. So dH is du plus PdV plus VdP. And the U is TdS minus PdV. So the PdV cancels. So dH is TdS plus VdP. This kind of substitution of differentials, working through this, you should really get very comfortable with, right? Whenever I give you a function or you set one up yourself, you should be able to very quickly go to the total differential. But what does this tell us, right? It tells us that variations of H come from variations of S and P, which means that H is a function of S and P. So what this did is that we started with a function U of S and V, and we went to a function H of S and P. So the variable dependence has changed from the extensive variable V to the intensive variable P. And where you can see mathematically where that comes from, right? It comes from essentially subtracting the work product minus PV, but it's minus P, so it becomes plus PV. And that's what's called the Legendre transform, and we'll elaborate on that a little more. So let's do this for F. So F is U minus TS. So dF is du minus TdS minus SDT. Again, you can figure out what U is, right? U is U is TdS minus PdV. So that means that dF is equal to minus SDT minus PdV. Or F is a function of T and V. In each case, you can also write the equations of state, right? The intensive variable here, the thing in front of the differential, has to be the derivative of the potential with respect to the variable in the variation. So here, that means that the first equation of state is that T is dH ds at constant P. And V has to be dH dP at constant S. So those are the equations of state in the enthalpy formalism. I can take them in the Helmholtz free energy formalism, so I would have that minus S is dF dt at constant V, and minus P is dF, minus P is dF dV at constant T. And here you're starting to see things that become a bit familiar, right? Pressure, or the negative of pressure, is the derivative of the free energy with respect to volume, right? Which is starting to be a lot like equations of state that we're familiar with. The last one, if you do this for the Gibbs free energy, is probably the most interesting, right? So G is U plus PV minus TS. And now if you work out the differential, and I'll let you do that, right? You'll find that the differential of G is minus S dt plus V dp. Which means that the equations of state are that S is minus dg dt at constant pressure, and volume is dg dp at constant temperature. Right. So what you're starting to see here is how the equation of states carry properties in them, right? Because this is essentially mostly a mechanical equation of state, right? It's telling me how I will get volume as a function of pressure and temperature, right? Because G is a function of temperature and pressure, so its derivative is a function of temperature and pressure. So what I will get out of this is some function V as a function of T and P, right? So this equation of state will embed mechanics, right? How volume changes with pressure, but it will also embed thermal expansion, how volume changes with temperature. Whereas if I look at the first equation of state, the one for S, so I will now get S as a function of T and P. And that will tell me how S behaves with temperature, which, as you know, embeds the heat capacity. And it will tell me how S behaves with pressure, which is a bit of a mystery what that's going to tell us, right? But we will later see through what are called the Maxwell relation that the behavior of S with pressure is related to the behavior of volume with temperature. Okay. So let me actually do that now. Let me expand a little on the equations of state in the Gibbs free energy formalism. So as I told you, you can sort of see that heat capacity is going to appear in here. And the clearest way to see this is take the differential of the equations of state. So if I take ds, so I'll get that this is ds dt at constant p dt plus ds dp at constant t dp. And let me do the same for the volume. The differential of the volume is the change of volume with temperature at constant P plus the change of volume with pressure. Sorry, I forgot a dt here. Plus the change of volume with pressure at constant T dp, right? So this is just math, right? I'm writing out but now you see that the properties show up, right? Now you see it explicitly because here we have ds dt. And remember, T times ds dt is the definition of the heat capacity. So this thing here is Cp divided by T, right? What is this thing? I think we actually haven't explicitly defined this, right? But as you see, this is going to tell you something about thermal expansion. So the volumetric thermal expansion, alpha V, is defined as 1 over V dV dt at constant pressure. So no surprise, right? This the temperature depends on volume, but you normalize by volume, right? So that this becomes a property that doesn't depend on the size of the system. So what you find is that this here is equal to alpha V times V. To be honest, to do this properly, I really should have normalized these guys all because otherwise mole numbers show up. So I should really do this all per mole, and it's a little more rigorously.
Good.
So
could you change to a different color marker? It's really
sure.
faint. Thanks.
I'll throw it away. Okay, so this is Cp, is that better? Cp over T, and this is alpha V times V. Is that better?
Yep, thank you.
Okay, cool. So what is Dvdp? That we've seen, right? That's compressibility. Right, the compressibility beta T is minus 1 over V dVdP at constant T, right? The minus sign because volume goes down with pressure. So this here is minus V times beta T. So later we'll see that the mystery property, actually we'll see it later today, that the SdP, because of symmetry in these second derivatives, is the same as this one. But today, we don't know yet what this guy is, right? Just to think a bit ahead, right? What I've shown here, so here I've shown that the equations of state, right? Entropy and volume, they are first derivative of the Gibbs free energy. Here we're taking first derivatives of the first derivative, so these are second derivatives. So what you're really recognizing here that I have the matrix of second derivatives, right? Since S is the first derivative of G with respect to T, what I really have here is d squared G dt, right? T squared. So we'll go into this a little more later, but properties of materials enter as second derivatives of the potential. The Hessian, or the matrix of second derivatives, essentially controls is where all the properties enter. And we'll formalize that a bit later. This is where I wish I had a lot more board space, but okay, let's try this. Because it would be great to keep this, but it's not going to happen. Why? So what you saw when we went between different potentials is that we're essentially changing the variable dependence, right? The internal energy and the entropy are defined as being only functions of the extensive quantities. So transformations like this, in which you transform functions of extensive variables into functions of intensive variables, or vice versa, are called Legendre transforms. And there's a nice description of Legendre transforms, both in Desfontaine and in Callan, to be honest, probably nicer than I can do. But they are transformations at least in thermodynamics, there's a more general definition of Legendre transform in physics. There are transformations to functions in which extensive variables are replaced by intensive variables. And really vice versa. You can go from intensive variables to extensive variables. Okay, so in general, if we start with the internal energy as a function of entropy and xi, so think of xi as a set of extensive variables, right? It's not just one. then I could define the Legendre transform phi as U minus one particular conjugate pair yi xi. And that will lead to a characteristic function. So the function phi will be a function of S, all the xj that you didn't Legendre transform. So the xj that are not equal to I and yi. All right, so that will be your new variable dependence in the Legendre transform. Can you see this happen? You should think about this, right? That you don't sort of think of this as some stupid formula. Why does this happen, right? Because let me write a corner. When you write du, right? Du will have a bunch of terms because you have a bunch of possible extensive variables here. But at one place in u, there will be a term yi dxi, right? So then when I Legendre transform, when I do this, if I take d phi, I will get du minus yi dxi minus xi dyi, and this will cancel that, and so I will now have dependence on yi. So it's kind of trivial that this happens, right? If you look at it that way, because you're basically switching the differential. So you can combine multiple Legendre transforms, right? You can do this many times. You can do this with a bunch of conjugate pairs. And so that will lead in general to some function, I'll call it f, as a function of s. So I haven't Legendre transformed with respect to t, I guess. Some j equals 1 to k xj. So these are the non-Legendre transformed variables. And then some j is k plus 1 to, what did I call it, n of the yj, right? So this is the set of intensive variables. And this is the set of extensive variables. Why do you think this is important? I'm going to give a bit of an intermezzo on Legendre transform, but you can kind of already see where this is heading, right? If I have a potential, a thermodynamic potential, in which I control a bunch of extensive variables, this set here, j is 1 to k. That means if I control xj, that means that work channel is not active, right? That means I'm not doing energy transfer with respect to xj. I'm not using variations in xj to do energy transfer. So the energy transfer in and out of the system will only come from these guys, right? Because my potential, how will my potential look like? My potential will be U. My guess is pink's not a good color too, right? Ah, I love colors. Okay. The Legendre transform will be U minus what? Some j is k plus 1 to n yj xj, right? So you see why this all goes together, right? Here I'm minimizing a function that includes all these energy exchanges, right? All these potential energy terms with the environment, except the ones that are constant, because they don't have an exchange, right? Anyway, I'll summarize that neatly in a bit, but I'm just trying to keep you awake. So why do we do Legendre transforms? Because if all you care about is doing the substitution from extensive to intensive variables, you could do that a lot easier, right? If all I want to do is go to change u as a function of, say, s and v, if I just want to go to t and p, that's actually a lot easier. Let me show you how you would do that. So if I have a function u, let me first do it with one variable here, right? As a function of x, and x is an extensive variable. So what I want to do is, so I have ux. And what I want to do is I want to go to some function u prime of y, where y is the intensive variable. That's actually easy, right? What would I do? Well, I know that y is the partial of u with respect to x. So that's some function y of x. So if I solve this, I get x as a function of y, right? And I substitute that in there, right? I get x as a function of y. I substitute in there, I have a new function of y, right? So it's trivial to switch variables in principle. The problem is that once you've done that, you cannot go back because you've given up some information. Right? Because let me show you that if we want to go from u prime as a function of y, we want to go back to u as a function of x. Really, what we're saying here is that what we have is a function u, which is u prime as a function of y, and y is the u dx. Right? This is the translation of what I've written here. And what is that? Well, that's a messy differential equation, right? Right, so u prime is some function. I have no idea what it is, right? It could be cosine, sine, exponentials. So I have a function of the derivative of the function I want, u with respect to x. So this is a messy, could be in principle, very nonlinear differential equation. Now, again, in principle, that could be solved, but I will always miss constant information, right? Because I only have information on u as a function of x. So all these functions, if I plot ux, right, this is my function. All these functions that I translate, these are different functions, u of x, but they are the same functions. These are all the same if you write them as u prime of the derivative. Sorry, u du dx, right? Because you have a bunch of values of x, let's take sort of dashed line here, right? In each of these values of x, the derivative is the same, right? That's the u dx. And the value of u is the same. So I cannot distinguish these functions. These are the same u as a function of du dx. So basically, I've lost constant information, right? So all this to say that when I substitute a variable by its derivative, I've lost constant information. So what does a Legendre transform do to solve that problem? Well, if you think about it, right, a Legendre transform tells you not just the function, but it tells you u minus yx, right? So you have some new function. Phi is u minus yx. What is u minus yx? Well, that's the intercept, right? If you're in this point, that's this intercept. So Legendre transform specify this series of curves because they're all equivalent, but then it also specifies the intercept so you know which curves you have. So that's why in principle, and not just in principle, Legendre transforming preserves all information. So a Legendre transform allows you to go to in a natural way to a function of different variables while preserving all the information. So I know it's a bit of a mess, so let me summarize this. Why this is all useful. Okay, so I'm going to abbreviate Legendre transform as LT. So a Legendre transform gives a new function with extensive variables, with an extensive variable, if you do it just for one term, substituted by its conjugate intensive. True. A Legendre transform preserves information which a normal substitution of variables doesn't. And a Legendre transform is also the equilibrium thermodynamic potential for systems that interact with their environment, and more specifically, for the system which is controlled by the natural variables of the Legendre transform. Okay, I know that's a lot to swallow, but this is a complicated sentence, but really, if you think about it, right? So, for example, if we go from U as V, at some point we went to F TV, right? We went to a function of temperature and volume, and this is what you minimize under constant temperature and volume, right? That's what it means, right? The Legendre transform. If I Legendre transform further and I get G as a function of T and P, Gibbs free energy is the potential that I minimize under constant temperature and pressure, right? So the way you set up an equilibrium condition, an equilibrium function, thermodynamic potential, is to go to the relevant Legendre transform. And again, don't think of this as pure math or rules, right? This makes sense, right? Because if I'm at constant temperature and pressure, again, then I'm not just minimizing U, right? I have to include the potential energies that my system has in the temperature and pressure field, which is minus Ts plus PV, right? So this is all super logical, right? I mean, in the end, equilibrium conditions in general, right, are completely logical, right? If you can exchange energy with the environment, that means you are coupled to the environment. Then you have to include that potential energy in your optimization. And that's what a Legendre transform does for you, okay? So you can do this now in all generality, right? We've defined 4 potentials, this one plus the enthalpy, right? But I'm going to teach you how you do this for any conditions, right? You can make 1,000,000 potentials. There are as many thermodynamic potentials as there are relevant thermodynamic boundary conditions. Okay, so just to be explicit, let's write it down. And then I'm going to do an example. So I'm going to write down the recipe, but I hope you understand why this is the recipe, right? So how to find equilibrium conditions for any system. Okay. The first thing you do is you look at your system and you define the constant and non-constant extensive variables, right? So define the constant extensive variables and the non-constant ones. Right? The non-constant ones are the ones that couple you to the environment. So for the non-constant ones, you have to do a Legendre transform. So for the non-constant extensive variables, you have to do a Legendre transform. And so you're going to define an object that looks something like phi, which is sort of my general letter for a thermodynamic potential, is U minus some I, yi, xi, right? And this just a little bit in pink, okay? This sum goes over the set of non-constant extensive variables, right? Okay. 3 is obvious. Phi is the relevant thermodynamic potential that is minimized. And what is number 4? What is step 4? Think about that. How do we actually minimize the thermodynamic potential? Remember, what we minimize over is the internal variations. So what you have to do, you have to write the differential of phi, d phi, in terms of the allowed internal variations. Right? And then you find the condition where phi cannot be lower anymore. So these 4 steps are the general way that you think of equilibrium in thermodynamics. And I hope what you get out of this that, you know, whereas when you first learn thermodynamics, you may have thought of these as kind of recipes. Oh, I minimize G when I have constant T and P, and I minimize F when I have constant T and V. But in the world of materials is much richer, right? If you understand the general way to set up equilibrium conditions, you can take on any system, right? You can take on any system with constraints in semi-equilibrium. For example, you could define a system that can exchange some species with the environments, not other species. You can define a system that's epitaxially constrained, right? A system that is constrained in 2 dimensions by epitaxy, but not in the 3rd one. Right? So you can set up whatever you want here, right? You can set up a system if you have a thin film, if you want to do thermodynamics of a boundary layer, right? remember that a big system, an infinite system, has to be charge neutral, but a thin layer doesn't, right? So you can set up systems at constant potential, right? Not at constant neutral charge. You can do anything you want now, right? So just as a sort of test case, I'm going to walk you through one example. How are we doing on time? Okay. Just to show you how this works. We can't actually sort of do complicated materials equilibria yet, since we haven't seen enough of the property matrices for that yet. But so let me take the following example. I'm going to take a bar that's clamped between two solid walls. Right? So these walls are immovable, but the system is otherwise under constant temperature and pressure. And I'm going to define the directions here. So the cross section, let's say this could be like a bar. This is the cross section is square. So I'm looking at here from in the cross section. So I'll call this LZ. So this is the Z direction. I'll call this length Y. So this is LZ here. And then I'll call this direction X. So this is the length in the X direction, right? So what are my extensive variables? So I'm going, over time, you're going to learn to just write down the equilibrium condition here. Trust me. But I'm going to work you through sort of definition of all the relevant variables, right? So what are the extensive variables here? Well, since I'm at constant temperature, right, entropy is involved. And the other extensive variables are the dimensions, right, which together make the volume. So normally we would have volume, but now because my constraints on these different directions on X are different than the constraints on Y and Z, I'm just going to write it out as Lx, Ly, and Lz. So in the most general terms, if you were to be asked to write down the first law for the system, with these extensive variables, what would it be? Well, we definitely have TdS, right? The exchange through the heat flow. And then in the X, Y, and Z directions, I essentially have mechanical work that's force times displacement. Right? If there's a force on the system and it displaces, force could come from the pressure, could come from something external I apply. Okay, so let me write that down for the X direction. So I'm not making any statements yet about the actual boundary conditions. I'm just writing down the general term. So this would be Lx, the epsilon x, right, the normal strain. And that's because just of the way I defined, right? I'm going to define that the differential of strain is the differential of length normalized by the length times the force, and the force is the area, which is Lz times Ly times the stress in the sigma direction, right? So this here is area, right? And this here is dl, right? So I get force because I multiply the area by stress times the change in length. Okay, and you'll see something that very often comes out, right? You get Lx, Lz, Ly, so that's the volume of the system here. So as you see, these three here will reduce to the volume. So I can do the same in general for the other terms, right? I will always get Lx, Ly, Lz times the epsilon y, sigma y, And then I will have a term that's Lx, Ly, Lz times the epsilon z sigma z. And I'm going to make use of the symmetry here just to make it simpler, right? That everything in the y and the z direction is the same. So I'm going to assume that the symmetry of the stress is not broken here. This is sort of less important, that sigma y is equal to sigma z. So can now reduce du to write it as TdS plus V sigma x d epsilon x plus V sigma y d epsilon y plus d epsilon z. So this is the first law differential. We could have just made this up, right? Because I haven't assumed anything about the boundary conditions, but look at this, right? Do you remember in the first or the second lecture where we calculated mechanical work? If sigma x and sigma y were the same, right? If I were in a pressure field, then I just get the epsilon x plus the epsilon y plus the epsilon z times the volume, and that's dv, right? It's the diagonal elements of the strain tensor times volume, so I get dv. So basically, this is a complicated version of what becomes pdv in a system, an isotropic system under pressure, right? But here we have it separated because there's the chance that stress builds up in the x direction that's very different from the y and the z direction, which is why we separated them. Okay, now comes the thinking part. So sit in your thinking chair. What variables should you have here in your thermodynamic potential? Remember that the variables that you need in your thermodynamic potential are the ones that you control, right? Because they are the boundary conditions. So what you control here? I think I want the answer from you. I'm going to do one. I'll take an easy one. T. And a few more. What do I control? Come on. What do I control in this situation? Think about, let's take an easy one. Think about the z and the y direction. What do I control at the boundary? I control the stress, right? Because it's equal to the pressure, right? So at the y, in the y and the z direction, I control the stress. So really what I control is sigma y and sigma z, right? Because they are equal to the pressure. Later we'll set them equal to minus p, right? But what about x? What do I control in the x direction? In the x direction, I do not control the stress. I control the length, right? Depending on where I set my walls. So the control variable in the x direction is epsilon x, right? So I have this twisted boundary conditions, right? That in two directions I control the stress, in the other direction I control the strain. So what is the relevant thermodynamic potential now? Well, I have to go from these variables to these variables. And by the way, epsilon x is the same as controlling Lx, right? It's just a normalization. So how do I go from here to here? I have to basically get rid of these extensive variables, right? By a Legendre transform to get to their intensive variables. So I need three terms in my Legendre transform. So what is my thermodynamic potential going to look like? It's going to be U minus Ts minus V sigma Z epsilon Z minus V sigma Y epsilon Y. And that, my friends, will be a potential, if you do the differential of this, which I highly recommend, of T epsilon X sigma Y and sigma Z. So that is your new Gibbs free energy. And please try to do this, but again, after a while, you should be able to write down exactly what that differential is, right? What is the differential of phi? You can do this by taking the differential of this, substituting in what du is, but I'm just going to do it for you right away. So that's going to be minus S dt plus V sigma x the epsilon x, because I have not Legendre transform with respect to the x direction, plus V times epsilon x plus epsilon y times dp. And I've now assumed here, I've set equal that p or minus p is sigma y equals sigma z. I personally think this is really cool. So you see how you can do this on anything, right? If we just learn to write out the work terms, right, which is what we did here, you just have to look at your boundary conditions and you can define the proper equilibrium function. Okay, let's make it more exciting. Even more exciting. Did you know that thermodynamics could be this exciting? At 8 in the morning? I bet you didn't. So let's say your advisor asks you, what's the relevant heat capacity here? I want to try to raise the temperature of this thing, right? So I kind of need to know what heat to put in. So what's the relevant heat capacity? And unfortunately, like if this is like a block of aluminum or something, you're only going to find Cp, maybe Cv in the literature, but probably only Cp. But what you really need is the heat capacity under this twisted boundary condition, right? Constant x direction, strain in the x direction, sigma yy, sorry, why did I not suddenly write two indices? So constant strain in x, constant stress in y and z. That's your relevant heat capacity. So that is defined through the entropy as the derivative of S with respect to T at those conditions, with those constraints. And then the question is, what does this become, right? I mean, it's obviously not Cp, right? It's obviously not Cv. Looks to me like it's going to be in between somewhere, right? Because I have two stresses constant, so that makes it kind of close to Cp, but I have a strain that's constant, so that makes it closer to Cv. So my guess is going to be somewhere in between, right? Because in Cv, I hold the three strains constant, because I hold the volume constant. In Cp, I hold the three stresses constant. So it's going to be somewhere in between, right? Okay. Time to wipe the board. So This is everything you need to know to set up equilibrium. Again, right, so what we've systematically done is we walked you through how to quantify work exchanges with a system. And now we've led you through how to set up an equilibrium condition for a system. So what I'm going to do in the next chapter is really just identify and highlight sort of interesting mathematical relations in thermodynamics that will help you along in doing this, but they won't really bring anything fundamentally new. In some sense, all the fundamental things there are to tell you that I can tell you in thermodynamics, I have told you now. And you could kind of take it from here, but we're going to help you along. But we're sort of done with postulates, with adding information to thermodynamics. So the last part of our formal introduction to the classical aspect of thermodynamics is to highlight some of the mathematical relations that exist in thermodynamics and which can be remarkably helpful when you try to find information about a system. So mathematical relations and transformations in thermodynamics. And this is the stuff you use in derivations and stuff, etc. And I got to tell you that for a long time when I did a mathematical derivation, it felt like a random walk. I would find some relation between P and T and I'd substitute that in and I hope that I get to the answer. And what I'm going to try to show you this lecture, but mainly next one, which I guess is next Monday, is that there's sort of a highly systematic approach to doing derivations in thermodynamics. And this is one of the great strengths of thermodynamics, right? The mathematical relations arise directly because we integrate different fields in the same setting. We integrate them through their contributions to the energy differential. And this stuff will relate, the weirdest things will be relatable, right? So for example, this derivative that we've encountered, change of entropy with pressure at constant temperature, this is extremely hard to determine experimentally because we really don't have an entropy meter, right? You know, we have a volume meter, we can measure the dimensions of things, but we don't have an entropy meter. We will see that that's equal to exactly the change of volume with temperature at constant pressure. Which is, when you look at it, a remarkable relation, right? Why would volume with temperature have anything to do about entropy with pressure? And these relations will be remarkably useful because this is measurable, right? This is thermal expansion. And if you do statistical mechanics, this will be very computable. So it will help us also when we build the relation between classical thermodynamics and statistical mechanics. You know, we're going to prove stuff that like Cp minus Cv, which would have been handy to do that problem over there, is Tv times alpha squared V over beta T. Again, it's a preview of what's coming next in this thriller. Do you remember, like, I think the first or the second lecture where I asked you, is Cp larger than Cv? You have your answer now, right? Because what this is saying is that the difference between Cp and Cv is a bunch of positive quantities, right? T is positive, V is positive, and the thermal expansion indeed appears just like we expected, except it appears squared. So it turns out that even when our thermal expansion is negative, we will find that Cp is larger than Cv, which is kind of weird, right? Okay, let's do this. How can we prove all this? So I'm going to walk you through a set of useful mathematical relations. And then probably next lecture, we'll try to do some cutesy problems with it. Okay, first one is what's called the Maxwell relations. Which state that if you have an exact differential of a function, of some function which I'll call f, function say of x and y, then if you write the differential df, so if you have an exact differential, then you know the first partial derivatives. This is m, this is n. And the Maxwell relation is a statement that the m dy at constant x is equal to the n dy, the x at constant y. And that's easy to prove. So let me take the m dy at constant x. M itself is the first partial of f. So this is d dy of the f dx. So this is equal to d squared f dy dx. And the n dx at constant y, this is d dx of the f dy. So this is d squared f dx dy. And if the order of differentiation doesn't matter, so if your functions are continuous, then you're good. So these are the same then, right? So that proves the Maxwell relation. Need to stay here? Go down. Yes, come on, camera, go down. There we go. Not very patient, okay. So let's apply that to the differentials we already know. So du is t ds minus p dv. So I can apply the Maxwell relation to that. So that's telling me that dt dv at constant s is equal to minus dp ds at constant v. And you can sort of do this for every potential. The most interesting one is when you do this for g, because dg is minus s dt plus vdp. So the Maxwell relation is that the s dp at constant t is equal to minus dv dt at constant p. And this is exactly what I wrote on the board before, right? And if you look back through your notes, this is proving that which was the SDP is the same as thermal expansion, right? Which is kind of remarkable when you think about it. In the PowerPoint slides that we put on Piazza, I put for the 4 thermodynamic potentials, I put down all the Maxwell relations. So for U, for H, for F, for G. And one thing you should notice is that they're very easy to remember. Here's the way I like to remember them. There is there are all kinds of mnemonic rules in books, but I think that the best way to remember their general structure is to see the following, that these always have the same structure. You're taking the derivative of something and you're holding its conjugate constant. That's always true. See, here it's dt, and you're taking that constant s. Here it's dp, and you're taking it constant v. Here it's ds, and you're taking it constant t. And you're taking the derivative of this quantity with respect to some other variable, v. And what appears here is the conjugate of that, right? So these are conjugates of each other. And if you think about it, that comes from the fact that these are taken from thermodynamic potentials. But so the general structure is that you take a derivative, a partial derivative, dx dy. I just write x and y here. X and y are now not in a conjugate relation. And what is constant is the conjugate of x. Right, so that's on one side of the equation. And that is equal to plus or minus. So what goes here has to be the conjugate of this. So this is the conjugate of y. And what goes here is the conjugate of x. And what are you keeping constant is the conjugate of y. So that's y again, right? So I just taught you how to write down any Maxwell relation that you may want to care about. And so the only thing you don't know is the plus or minus sign, right? So you can invent any Maxwell relation you want. How do you know what the sign is? Some of you will come up with your own tricks, but the way I do it, well, since you're taking derivatives with respect to these variables, right? This has to come from the potential that has these as variables, right? Because Maxwell relations come from a differential. So if these are the ones that you're taking derivatives with respect of, it has to be the potential in those variables, y and the conjugate of x. So for example, let's say you're in the middle of a derivation and you see something that's ds dv at constant t. First of all, you decide whether there is, I call it Maxwell bait or not. If you take a derivative of something with respect to its conjugate constant, then you have potential to use a Maxwell relation on it, right? So, and without even looking at your cheat sheet, you know that this is, you know what this is going to be equal to, right? This is plus or minus the conjugate of that, so that's p, and the conjugate of that, so dp dt, and I have to keep the conjugate of this constant, so v. So I've just written out what the Maxwell relation is, right? How do you know the sign? Again, when you're fast at this, you'll figure this out, what the sign is. But, you know, let's say I don't know. So it has to be a potential that has v and t as variables, right? Because that's what I'm taking the derivatives of. So if I have v and t as variables, that means it has to be the Legendre transform of u minus ts, right? Because u would have v as a variable and s, but I need to go to the conjugate t, so I do minus ts. I work through this, and I would get df is minus sdt minus pdv, right? If you do this, and so you would see that if you take the Maxwell relation of this, you would end up with the plus sign because you got two negative signs, right? So there's a whole logic that's sort of self-contained here, right? That yes, you can use your cheat sheets, but I might just give you boundary conditions that you haven't seen before, right? I might come up with some crazy situation like the bar clammed between walls and ask you to derive the relevant potential, the relevant Maxwell relations for that. So you can easily extend this to systems with more work terms. So let's say multiple work terms. Let's do magnetism. Okay, so my du would be T ds minus P dV plus H dm, and I don't know, am I carrying, I'll carry the mu naught around, here we go, plus H dm, right? If I have magnetism, that's my magnetic work term. Let's say I go to a new thermodynamic potential, I'll call it G star, which is in all the intensive variables. So because normally I control temperature, pressure, and an applied field, I don't control the magnetization. So this would be defined as U minus Ts plus PV minus mu naught HM, right? That would be my relevant potential. How would the differential of G look like, or G star? Try to practice this a bit, right? So you don't always have to spend too much time on this, right? That would be SDT or minus SDT plus VDP minus mu naught MDH, right? Again, you would take the differential of this, substitute what the U is, and here's what you would get, right? So what are the Maxwell relations now? So I can do this Maxwell operations. I have 3 differentials. I can do it 2 at a time. So I have the number of Maxwell relations is 3, choose 2. So it's 3, right? So for example, I'll have the old Maxwell relation there. If I do ds dp, I'll have ds dp at constant t, and h is equal to minus dv dt at constant p and h. That's the first Maxwell relation, right? So it has the same structure as what I wrote down there, but I've just added a constant. I'm keeping also the applied field constant, right? You can write out more Maxwell relations, right? And there's a few interesting ones, right? So here's a new one that comes in. If I take the derivative of mu naught m with respect to t at constant applied field and pressure, and this is kind of a property that I may want to know sometimes, right? It's how magnetization changes with temperature. Just for example, what's sometimes expressed as the Curie constant. Or so this is equal to ds dh at constant t. So we've just expressed that the change in magnetization with temperature comes from the change of entropy with applied field. And there's another one that I'll talk later about. There's one that crosses volume with field, with a magnetic field, right? I'm going to get something like dV dH is dmdP. And dV dH is kind of neat, right? You're asking the question then, how does volume of a material change with a magnetic field? And I'll show you a cool example that in the next lecture. So, because that's actually a useful property in materials. Okay. We are almost out of time, so let me do one quick example on an ideal gas, and then we'll pick up the pace on Monday. So for an ideal gas, we've learned to calculate entropy changes in many ways, but I want to show you that it's consistently getting easier, right? So if you do an isobaric or isochoric problem, then it was easy because you know the heat capacity. So if you do an isobaric temperature change, right, then ds is just Cp dt over T. But if you do compressions, then both pressure and volume changes, so you cannot integrate the known heat capacity. So let's say we do an isothermal pressure change, right? So isothermal compression or expansion. We've already done this in many ways, right, before. Remember the way that we did it the first time? We said, well, if it's isothermal, that means du is 0. And if the u is 0, that means del q is minus del w. And that's how we got, and then we integrated that. I want to show you that now it's much easier because I can literally write this. I can write this question as a partial derivative. What I'm really asking is, what is the partial of S with respect to P at constant T? Right? Do you see that this question is the same as that, right? I've just put it now in a mathematical terms. Well, I have no idea what that is, but I can right away see this as Maxwell bait, right? This is equal to dV, because V is the conjugate of P, dt at constant pressure. And actually, if you get the right Maxwell relation, it's minus. And why is this good? Because the equation of state for ideal gases tells me exactly what dV dt is, right? Because V is nRT over P, right? So dV dt at constant P is nR over P. So this here equals minus nR over P. Or if I break open the differential now, what I'm telling you is that ds at constant temperature is minus nR dP over P at constant temperature, which is what we found the last time. It's good that we found the same thing. But I can now right away calculate how entropy behaves because I can take the total differential as part of an, first of all, under constant temperature with a pressure change, and then under constant pressure with a temperature change. So I can just expand it into these two partials. Okay, this is just math, right? And I've just proven what that one is. So this one here, of course, is Cp. This is going to lead to Cp dt over T. And this one I've just proven. This is minus R dP over P. And I've dropped the N, so I'll write this as ds, right? So you now have a more mathematical way to relate to write out the differentials of quantities, right? So I've written out here mathematically what the differential of S is, but now through the Maxwell relations, I often know what these partials are, and I can turn them into property information, right? Which is an equation we've derived multiple times now, but you can see you can now do it through Maxwell relations. Okay. Kind of a little behind here, but it's 9:29, so it's time to stop. Good seeing you all again. I hope you get outside. Smoke is almost gone. Make sure you take some time off. Friday is a discussion section. I will also have my office hours. I had one person last time, so I'm really happy. Again, if you need to talk to me at any other time, just let me know. And otherwise, I'll see you all on Monday. So enjoy your weekend. Take care. Bye.